Latitude Media, podcast at the frontier of climate technology.
On the way to maturity, the clean energy industry has gone through many different cycles of hope, hype, dead ends, and rebirths. George W. Bush was pumping up the hydrogen economy more than 20 years ago, mostly for cars. We all know how that turned out. Do you know anyone who drives a hydrogen car? But here we are in the middle of the 2020s, and hydrogen is back in favor, this time for industrial uses. Cheap renewable electricity made green hydrogen more feasible, which is starting to drive mass production of electrolyzers. And the question is, will the industrial demand be big enough to drive the market? Many people think it will. In the 1980s, the hottest technology in renewables, literally the hottest, was solar thermal. The U.S. Department of Energy supported hundreds of megawatts of parabolic trough collectors. The most common kind were different-shaped mirrors that concentrate the sun on a heat transfer fluid. They generate steam, and then they run a Rankine cycle turbine. It was the first utility-scale solar tech. But costs were really high. Early developers went bankrupt in the 90s, and wind took over as the large-scale renewable of choice. Fast forward to the mid-2000s. A computer scientist named John O'Donnell had freshly sold the semiconductor company he'd co-founded, and he was looking for the next venture. John had worked on a fusion program early in his career, and so he turned his attention back to energy.
At the time, this is back in 2005, solar thermal delivered most of the world's solar electricity. It was far lower cost than PV. It was really set up for large-scale, utility-scale only, which I found attractive. Let's find ways for large flows of private capital to build big energy infrastructure now.
John co-founded a company called Osra. It used a less expensive concentrating solar technology developed in Australia. Later, he co-founded a company called GlassPoint, which built an enclosed mirror system designed to cut operating costs. And he wasn't alone. There were roughly a dozen companies that emerged in the mid to late 2000s, developing a wide range of utility-scale technologies to use heat from the sun to generate electricity. But there's a reason most of those companies don't exist anymore.
Now, over the 15 years that I worked in solar thermal, the price of PV solar came down 90% and far past it. You can use it almost everywhere in the world. The concentrating technologies fit only in a few places. And really the biggest issue, we built a project that had a 9-mile-long steam line. And we learned that you can move electricity 1,000 miles. You can move steam 1,000 meters.
Both of his companies ended up moving toward industrial steam rather than electricity. Osra was sold to the French energy giant Areva in 2010. It was later shut down after Areva couldn't make the business work. The second company went through liquidation in 2020 and was recently reborn as a steam-as-service provider. John distills his decade and a half in the solar thermal business to a simple lesson: don't be too innovative.
The world is full of folks who are perfectly happy to build and finance PV solar systems at very low costs of capital. If you are too innovative, if you can't turn to a standard construction company or EPC, if you can't bring a new technology with suitable guarantees to market, cost of capital that's too high will just kill any renewable energy project.
So you stayed committed to decarbonizing industrial heat. Why?
It's a quarter of all the coal, oil, and natural gas that we burn in the world is for industrial heat. We had a deep understanding of the problem and years of sort of failing. The IEA says we built more than half of the solar industrial heat that's running in the world, but it was a drop in the bucket. I mean, literally 0.3 gigawatts out of a 9,000 gigawatt market. It's a good first step, and we now have the market conditions to go do that at scale. Because everywhere in the world where there is intermittent energy that's cheaper than fuel is a place where this is going to take off and grow.
When John says this is going to take off and grow, he doesn't mean solar thermal. He means a heat battery. Today, he's CEO of a company called Rondo Energy that uses cheap renewables from the grid, electric heaters, and bricks to supply heat to industrial customers. And that cheap PV that made solar thermal so difficult is now a critical input for decarbonizing factories and processing plants.
If you're going to decarbonize that sector, the number one issue is Do you have a decarbonized source of energy that's cheaper than business as usual? And it was becoming clear that, yeah, PV and wind are pretty much everywhere in the world, intermittently cheaper than any other form humans have ever had available, including burning fuel.
This is The Carbon Copy. I'm Stephen Lacey. This week, we're tackling the industrial heat market. John O'Donnell, the CEO of Rondo Energy, talks about why he believes we can decarbonize the vast majority of the world's industrial heat by harnessing intermittent renewables, bricks, and heating coils you might find in your kitchen.
America's green banks are preparing to unleash a wave of capital for clean energy. The Greenhouse Gas Reduction Fund invests a historic $27 billion in projects nationwide. This could mobilize up to $150 billion of private capital for solar, storage, efficiency, and electrification in underserved communities. So how do we deploy those billions quickly, efficiently, and with the highest impact? On July 18th, Latitude Media and Banyan Infrastructure will host a virtual event exploring the on-the-ground realities of making America's green banks a success. Register for free by clicking the link in the show notes or go to latitudemedia.com/events.
So there are lots of different ways to potentially decarbonize heat. Industrial heat pumps, electric boilers, green hydrogen to replace gas, carbon capture, solar thermal. You're approaching it differently. You're using thousands of tons of bricks as a thermal battery to deliver heat when needed. How does it work, and why this approach?
First of all, why this approach? You mentioned two classes, I would say. One, the carbon capture path says you're burning fossil fuel, burn 30% more fossil fuel than you're using right now to capture the emissions from burning fossil fuel. We can stipulate that is not a pathway that's cheaper than burning fossil fuel. The other pathways, heat pumps and electric boilers, at different temperatures, use continuous electricity to electrify a load. And in today's world, in most places in the United States, you can get at most about 40% of your annual electric power from renewables, the balance by thermal power stations. A heat pump may get you about level with emissions from burning fuel directly locally, and an electric boiler will multiply your scope 1 plus 2 at least by a factor of 2 and maybe 3. But those two things have in common, because they need baseload electricity, they increase the demand on the grid during peak periods. They drive this narrative that industrial electrification is going to require us to build a lot of peakers, a lot more wires. And so they are all in sharp distinction against what Rondo is doing, which is let's build something that is very low cost per kilowatt, an energy storage system that can take all the energy needed for 24 hours of operation during 4 or 5 hours a day. If it's cheap enough per kilowatt that we can do that, now this is something that can be dispatched either by a system operator or a customer to follow the availability of generation, to absorb curtailment, to absorb otherwise negative price electricity, and never take a single kilowatt hour from a thermal power station. Only be taking power from renewables, moving more megawatt hours through the same megawatts of transmission lines, and open up all kinds of flexibility, including local generation, local islanded generation. Now, any electricity storage technology in principle could do that. We could do this at some price with lithium ion, of course, but hydrogen, lithium ion, all those things are doing electrochemistry. And when what we want is heat, we don't need to do chemistry. We can use the physics of heat transfer to do something much, much cheaper, store energy as heat in solids. You mentioned we use brick. We use brick because 200 years ago, the steel industry figured out how to use brick for high temperature heat storage to save coal. We use exactly that same material heated with the same heating elements that are in your toaster at home. slightly bigger ones, and found a way to, and when you heat a brick to 1,000 C, it stores as much energy per pound as a lithium ion battery, costs 10 times less, lasts 10 times longer. So we found a way with a sort of a physics insight to do something very simple to tie into this new emerging reality in electricity grids around the world. We can have as much intermittent power if we're agile about taking it at a lower cost than fuel. We can have as much as we want.
So when you install one of these heat batteries, like what kind of equipment are you replacing in an industrial facility? Are we talking about, replacing a boiler, a kiln? Like what is it replacing?
Yes, exactly. What is the existing heat source? If we're in the paper industry or processing food or refining fuels or making chemicals, the vast majority of our energy today comes from steam boilers. And those steam boilers hook up to a steam network. Our heat batteries make steam exactly the same way. They'll sit next to those steam boilers. You may run those steam boilers a little bit during the winter or on high-price electricity days so that you have 100% firm, but there's no change whatever to the facility. I was on a panel a while ago with the head of sustainability from a major consumer brand who said, my factory teams always hate it when the decarbonization team shows up. They want them to tear the factory apart and replace 6-inch steam lines with 36-inch water lines so they can use heat pumps and shut the factory down. This is a drop-in solution for anybody using steam. For cement plants and steel mills that use kilns and ovens, this technology connects to those, delivering superheated air. And there are some modifications to a kiln that was designed to run on internal combustion to now run on superheated air. We are working on those things with builders of kilns and ovens. We have a particular project funded in Denmark right now, but the race to scale is boilers everywhere. Just go replace that. That's something like 80% of industrial heat. It's more than that in the United States.
And why has industrial heat been so difficult to decarbonize historically? Is it purely economics? Is it because a lot of these manufacturing facilities or industrial players have such tight margins that they're purely focused on cost? Is it because these have not that these are not necessarily drop-in replacements historically and they require a lot of re-engineering? What have been the biggest barriers?
You mentioned them, the first two. That is, what we're doing at Rondo, we could have done 5 or 10 years ago, but it would have been stupid. Intermittent electricity at that time was far too expensive as a replacement for fuel, and there was less of a, shall we say, a corporate drive to decarbonize now, not decades from now. Having a solution that is cheaper than business as usual, not requiring a green premium, coupled with a drive to decarbonize, those two elements drive action at scale. There's been decades of the chief sustainability officer and the factory manager are at odds with each other because the factory manager is measured on cost of production. We're now entering this world where, on an operating basis, zero carbon heat is cheaper than fossil fuel heat. Those conditions, the availability of intermittent electricity at a price that's lower than the price of burning fuel, those conditions did not occur until very recently. So we're just past this tipping point. And one thing we know for sure, looking at grid models everywhere, we see what that future looks like. Someone said the future is already here. It's just not evenly distributed. Look at South Australia with 70% renewables in the system and almost 3,000 hours a year of negative electricity prices. Look at Oklahoma last year with more than 2,000 hours of negative electricity prices. Look at the Netherlands, where the hours of negative electricity prices have tripled in just the last 3 years. The Inflation Reduction Act, maintaining and extending the production tax credit, means there's tons more of that coming across the United States. What Europe is doing just in the electricity system is also driving that. The conditions are everywhere emerging now for this class of technology, these electric thermal storage things, heat batteries, to harness those conditions. And they are unique in harnessing them because they can be cheaper per kilowatt at charging. A Rondo heat battery is not a $2,000 or $1,000 a kilowatt electrolyzer that delivers heat at 50% efficiency. It's about $5 a kilowatt on a marginal basis for these electrical wire heaters. And it's 98% efficient at turning electricity into delivered heat. So we get pretty excited because, again, we are just entering this very different rate of deployment, just as we saw a different rate of deployment for wind and solar when they became cheaper than fossil generation. So they wound up in utility IRPs without mandates. That's the tipping point that we are on industrial decarbonization now.
It's such a great example of what you can do when you have cheap, abundant, renewable electrons. And you said that this would not be a feasible solution even 5 years ago. I'm wondering, when we think about both the benefits to the grid and to the industrial customer, how do you frame this? Do you think about it in terms of grid reliability, or do you frame it specifically around the unique industrial use case?
That's a great question. And the value to different participants in the energy system is different. We're working with EDP at scale in Europe. EDP is, I think, the world's largest owner of commercial industrial C&I solar. They're a major player building utility scale wind and solar. They have a substantial electricity trading and grid operations capacity. They're able to bring those skills together to monetize the value of flexibility and grid services, to trade in day-ahead markets, and to put together a very specialized kind of power purchase agreement for energy that's delivered when they're controlling the charging knob, so as to optimize the value of existing assets and new assets, and then put that together with their development skills and go to customers and offer customers a fixed price, long-term heat as a service contract. During our announcement just recently, the EDP commercial CEO said, this will make our average C&I project maybe 10 times larger and allow us to not just deliver 20% decarbonization to a customer, but 80%, cutting into their giant Scope 1 emissions and saving them money. So there was grid value, again, in having large, centrally controlled, and right now controlled, dispatchable demand. Jesse Jenkins is publishing a paper shortly exploring that. His paper findings really excited us because he found that in looking at systems that he modeled in the eastern side of the US, for every megawatt of heat batteries that show up in the system, between 1.2 and 1.9 megawatts of new renewables show up in the system. Intuitively, that's because heat batteries are absorbing curtailment, making a renewable project more economical. It can sell more of its power, soaking up what would otherwise be intermittent power. And those grid effects of causing more renewables to show up, that the heat battery is not using all those megawatt hours, mean that the total system carbon savings are approximately twice the savings at the project site. Industrial decarbonization this way has grid benefits, can deliver lower cost energy to the industrial, and leave alone or lower average electricity prices for others. That's kind of a holy grail. That's accomplishing both of those things. And in that sense, the volatility problems that grids have become a solution for industry. And industry's giant energy demand, if it's run through heat batteries, becomes a solution for the problems of the grid.
So if we think about that partnership with EDP, which links hundreds of megawatts of new renewables to these heat batteries and serves them to EDP's industrial clients, is that the kind of partnership that is required to scale this technology? Or, are you still going to industrial partners in sort of one-off relationships, or do you have to kind of create this portfolio of assets with large developers? What's the way to scale this technology?
What's the way to scale this technology is exactly the right question. And that's the one that we ask ourselves all the time. And there are a lot of different pieces of that. One of them, make it as uninnovative as possible. We use completely conventional boilers and electrical heaters, all sorts of things. The heat battery very closely is modeled on a conventional industrial boiler. Two, make sure that the storage media is available at scale. I think the EDP relationship is one perfect example of how this can go. A new tool in their toolbox lets them grow their business much faster, lets them, in fact, build utility scale projects that don't need to wait for utility scale grid connections. We can build them directly powering heat batteries near the point of use. So in the United States, our experience so far has not been that there is a developer community on top of this at scale. Across Europe, there are half a dozen utilities working on this at scale in half a dozen countries right now. In the US, there's a developer community's attention, in my humble opinion, has been a bit attracted to the hydrogen subsidies, and that the place will get the next wave of growth for utility scale solar. We'll be building hydrogen projects that sell hydrogen to somebody somewhere sometime. But these kinds of partnerships in the US, we think, can also unlock dramatic growth.
On July 18th, join Latitude Media and Banyan Infrastructure as we take a deep dive into the next phase of deploying the $27 billion Greenhouse Gas Reduction Fund. We'll provide practical insights for the state agencies and local lenders at the front lines of dispensing these funds. Where are the bottlenecks? How do we balance speed with transparency? And can America's green banks live up to the expectations of both local communities and Wall Street? Latitude Media's Stephen Lacey, Banyan co-founder Amanda Lee, and Clean Energy Fund of Texas EVP Billy Briscoe will answer these questions and more on July 18th at 1 p.m. Eastern. This is a must-attend for project developers and financiers. Register for free at latitudemedia.com/events or click the link in the show notes.
So you've been at this a long time, and I've been covering the industry since the mid-2000s, and I remember going to solar conferences where there were a lot more solar hot water systems on display than solar PV systems. There was a lot of glass and metal concentrating photovoltaics, parabolic troughs, big and small, and it felt like solar thermal was really going to dominate. And of course, as we outlined, that changed radically as solar PV costs came down with sort of brute force manufacturing and engineering. What makes this different, right? Where this is a very optimistic moment. You've got a technology that uses conventional materials and can drop into an existing industrial plant. But why are you so optimistic given that you've seen a technology that seems very promising not succeed because it got beat out by another technology or just didn't find its place in the market?
That's a great question. And we don't have to invent anything for gigawatts, tens of gigawatts, hundreds of gigawatts, thousands of gigawatts of renewable electricity to be built by a community that can finance and build at scale. There's nothing to prove there. In fact, that community is struggling with places where there aren't grid connections available. There are the marginal value of more solar generation in a solar location can be approximately zero if generation is happening when prices go to zero. There could not be a more amazing set of market conditions if you have a technology that can harness that. And, we do have electrochemical batteries that can move power from noon to 7 p.m. Their economic viability in many places depends critically on how high that 7 p.m. peak is, and it falls very rapidly with deployment of batteries in a zone. We have electrolyzers that in principle can operate intermittently, but because of their capital costs, they don't pencil operating at capacity factors typically below 50%. But it's 15 or 20% capacity factor electricity that we can have with spectacular economics in most of the world. Between wind and solar, we now have the conditions, the enormous growth in offshore wind, huge deployments of onshore wind in all kinds of places in the world, as well as the solar regimes. Tesla released an analysis last year that said that the world is going to have twice as much installed heat battery capacity as grid battery capacity of all kinds combined because of the size of this energy demand and this simple, low-cost way of serving it. Again, that's true because of what's happened with the primary costs of wind and solar power.
How should we think about the size and scope of the market for heat batteries? Like, what's the total addressable market? How much of industrial heat demand can these batteries serve?
People have looked at this from 2 or 3 different directions. That's exactly the right question. From a temperature standpoint, so electricity is electricity. You can convert power from 1 volt to 1,000,000 volts back and forth. Heat is not heat. If you're going to deliver heat at some temperature, you need to store it at that temperature or slightly higher. The temperatures that today's Rondo heat batteries deliver serve about 90% of all the industrial heat used in the world. The one exception is about 40% of the energy used in making cement. And the steel industry is flipping over from using coal to hydrogen, and most of that energy is not actually heat, it's chemistry, converting iron ore. So it's about 90% at the current temperature regime. If you look at that, Tesla's assessment, when they looked at the all-in energy demand, that's about 40 terawatt hours of installed capacity. Their assessment was that it's about $3 trillion of total for the industrial heat that was in use in the world 4 years ago, I think. Obviously, this is a sector, the industrial sector is growing as the world becomes richer and grows. So decarbonizing it, getting it onto this track of decarbonizing rapidly so we can just stay even is critical. And we see the path clear with what we're doing to decarbonize most of that within about 15 years, given the constraints on how fast wind and solar can be built. And there aren't meaningful production constraints on the brick materials that we use. The actual market at any given time, the right now market is, okay, how much of that industrialized world do the economics of electricity, are they in your favor on an operating basis? And, so we see that between now and 2030 moving, broadening. By 2030, in most of the industrialized world, the conditions that exist in the 6 European countries where we're developing projects now, in Australia and the half dozen US states, those market conditions exist in most of the industrialized world, that you can have intermittent power cheaper than fuel and cheaper enough than fuel to also overcome the financed cost of heat battery operations.
One thing that has really set the Biden administration apart has been its focus on industrial decarbonization. And the Department of Energy has funded a wide variety of initiatives around industrial decarb. One being the heat shot with a target of cutting U.S. industrial emissions by 85% by 2035. And the DOE also just unveiled $9 billion in funding for industrial decarbonization projects, including a couple projects that will use Rondo's heat batteries for beverage production facilities. What do you make of this strategy generally coming out of the Biden administration? And what are the levers of government support that are most helpful for this particular slice of the market?
The DOE decarbonization drive has just been phenomenal. The Biden administration is doing something that has never been done before. DOE has assembled expertise from across other portions of the DOE and the government focused on industrial decarbonization. One of the things that DOE, in all the applications materials and the evaluations, they said very clearly they're looking at things that will step and repeat. We're trying to build first-of-a-kind larger installations that will then directly inform ongoing deployment of that technology in that sector. That is super valuable because many industries, a technology may exist in some other industry, but it's until it's used in this industry, it just doesn't get attention. It's not believed to be credible. It doesn't wind up in people's strategic planning for the next factory or for the next overhaul. So we've been hugely excited to see the breadth of technologies that DOE is supporting. And yeah, we are being pulled into multiple industries by this program. And one of the things that was announced just this week was a deployment of Rondo heat batteries in the food and beverage sector with Diageo, who have been an innovator looking at every other decarbonization pathway for food and beverage. They've deployed heat pumps. They've deployed electric boilers. This support has created the drive for our first two heat battery projects that offer simpler, deeper, cheaper decarbonization and get over the, yes, all that's true, but the technology is still juvenile. It hasn't been used at scale in this industry. That's the impact of the support.
So the Department of Energy has a bunch of really ambitious goals as part of this broader Earthshot initiative. The big one was, of course, the Sunshot initiative, which looked to get the installed cost of utility-scale solar PV down to $1 a watt, and the industry hit that well ahead of target. And I think they've now updated that target to 3 cents a kilowatt hour for utility scale solar by 2030, which seems very doable. There are others, including $100 a ton of carbon removed by different direct air capture technologies. And then there's this industrial emissions goal to slash industrial emissions 85% by 2035. The point of these targets is that they should feel very ambitious, but also achievable. And I wonder what you think about that industrial goal. Does cutting emissions 85% in this sector in the U.S. within a decade feel achievable to you?
Absolutely. And those goals are related, and some of them might not be set high enough. Recent projects in the Middle East have seen utility scale solar at 1.3 cents a kilowatt hour. Now, with different solar radiation and different costs of labor and tariffs and finance costs. But there are goals that are clearly achievable. And that electricity goal is, of course, deeply connected to what is the fundamental cost of replacing fuel combustion with intermittent electricity. We already have big swaths of the country where it's economical to do that. And on the other hand, some places that are heavily industrialized are probably 5-7 years away from intermittent electricity being cheaper there. But that goal is the right one on the industrial decarbonization goal. We have the tools to do it. It is principally a matter of market education, permitting, making it possible to build the renewables, for example, to power these facilities, and alignment. Just some of these projects, an individual project may take 5 years from conception to COD, and getting those projects started, creating the policies to get them started, the IRA's mix of policies, the financial encouragement to get going, as I said, is very helpful, not just for the projects in this basket, but for a wider set of projects inspired by these.
If we think about what's happening on the grid today, we have a massive backlog of renewables. We have suddenly all this new industrial activity with ports ramping up and new production facilities and clean energy manufacturing facilities, data centers. Like, we're seeing really significant increases in demand around the country. How do you think about these heat batteries as part of the puzzle in solving this load problem that we are starting to see in the United States?
Yeah, this load problem, utilities in the United States are used to years of no growth. And suddenly, we're seeing huge shifts in IRPs. And are they going to go back to building peakers and another whole wave of gas-fired power plants? Or is that load growth going to be served by a huge uptick in building wind and solar? There is no inability to build the wind and solar. That is, we can make the panels, we can make the turbines, there's no issues. One of the big issues is, can those facilities be permitted? But of course, the real pivotal matter is, what are the economics? What are the techno-economics of the energy storage needed to deliver 24-hour power for a data center or a manufacturing operation or any one of these things? And heat batteries play an interesting role in longer duration energy storage. If you had asked me this question a couple of years ago, I would have said we are working exclusively with industries, but 2/3 of all the industrial steam in the United States is delivered by cogeneration plants that make electricity and steam in a single thermodynamic process and wind up exporting electricity to the grid as a side effect of making the steam that they use. Because we are the hottest thermal energy storage of any kind that's in commercial operation, we drive those same cogeneration trains at higher efficiency than they are today when burning fossil fuel. We don't have any emissions losses. So one way that we are finding ourselves participating in some of these things, there are places where an industrial cogeneration facility that's exporting fossil electric now, repowered with a large new wind or solar array tied into heat batteries, is going to become a new baseload source of clean power in that region on the grid. We have gotten pulled into the unique value that heat batteries can deliver in tandem with combined cycle gas-fired power stations and retiring coal-fired power stations, where in both cases, the round-trip efficiency, electricity to electricity, is higher than some of the other long-duration batteries, and also provides unique value in combination with those power station operations. It's an area, it's the newest area that our team is being pulled into as we're building larger and larger projects serving the electricity sector and the data centers in particular. It's not where most of our time is going. It's only a small portion, but it is very clear that there will be substantial impacts made from these very cheap heat batteries that, for example, a combined cycle power station can burn fuel 15% of the year, but be a completely intrinsically firm, high-efficiency generation asset from energy storage all year. When people think about replacing a power plant with batteries, they're typically actually replacing with batteries and a peaker gas plant. And we see here in California more and more operation of peakers replacing more efficient combined cycle plants. The the emissions trajectory of the electricity grid is moving in ways that we're just learning about as we engage more deeply with thermal power generation, where we see a role for heat batteries to turn that around.
What a fascinating space. I'm really eager to see how it evolves and hopefully quickly. John O'Donnell, the CEO of Rondo Energy, thank you so much.
Thank you so much, Steve.
And that is the show. If you want more about the topics we're covering here, go to latitudemedia.com. You've got show notes there that you can read. Our episodes are there, our back catalog, and tons of good coverage from our reporting team as well. The show is produced and written by me. Sean Marquand is our technical director who mixes the show, and he wrote our theme song. Latitude Media is supported by Prelude Ventures. Prelude backs visionaries accelerating climate innovation that will reshape the global economy for the betterment of people and planet. Their portfolio and investment strategy can be found at preludeventures.com. And I know that most of our listeners hear about this podcast from other people. That's just how we grow. And if you can pass on the word, we'd be really grateful, whether that be on social media or sending a link to a colleague or a friend. And thank you so much for that and for being here. I'm Stephen Lacey. This is The Carbon Copy.